I'm Dr. Marie Henderson, a planetary scientist at Goddard Space Flight Center in Maryland. I love the moon, and so I became a planetary scientist to study lunar volcanism and planetary imaging. In addition to that, I train astronauts in lunar geology as one of the scientists on NASA's Artemis II mission. The mission is due to launch early next year, and it'll be the first Artemis flight to the moon and back with 4 astronauts on board. Our science team will support them from Earth in real time as they make geological observations from the Orion capsule with both their eyes and cameras. You'll learn more about the Artemis II mission in the coming months, but for now, I want to invite you to join me, NASA, and explorers around the globe in looking up and appreciating our nearest celestial neighbor, the moon, as part of NASA's annual International Observe the Moon Nights. Enjoy the upcoming show where you'll learn more about the moon and NASA's lunar science and exploration plans.
I'm Reed Wiseman.
And I'm Victor Glover. And this is how we pilot the Orion spacecraft.
What are the differences between piloting an airplane and a spacecraft? I think the thing that I first think about is on a spacecraft, it's really all about attitude. It's really not about thrust and getting the airplane flying faster. The spacecraft is already going almost 38, 39 times the speed of sound. So we're really controlling the attitude. Where are we pointing? Where are we looking at out the windows? Where are our antenna and arrays pointing?
The software is the primary flyer of the spacecraft. I think that's the biggest difference, especially for a pilot coming into this who wants to get on the hand controllers and put the aircraft or the spacecraft in its proper attitude. In aircraft, the software is really helping the pilot, and I think now it's almost like we're helping the software.
So a couple of things we're going to do on Artemis II, right after liftoff, we are going to detach the Orion spacecraft and service module from the interim cryogenic propulsion stage, which is just a lot of words for our upper stage. During that, Victor will be physically flying with the rotational hand controller, the translational hand controller, and doing station keeping on this upper stage.
This phase of the testing will be to simulate the flying that we would do if we were docking to another spacecraft like our lander or to our gateway. I think we should show you how we actually control the vehicle. So we've been using terms like rotational hand controller. Rotational hand controller, we say RHC for short, and translational hand controller, THC for short. In an aircraft, you would have a stick and a throttle, but it's the things that you put your hands on to control the spacecraft. We will pitch, roll, and yaw. Those are the 3 axes in each direction. And then we will also go up, down, left, right, in, and out, and we will assess how precisely that we can control the spacecraft. But we mentioned earlier that the main controller of the spacecraft is software. And so the main way that we interact with the spacecraft is our
cursor control device, your absolute favorite. I know you love this
CCD.
thing. This thing, it looks awkward, it looks weird, but when you get to use it, it's actually a genius piece of gear, and I know it is your favorite.
Oh, it is. This is our primary way to interact with the spacecraft. And so what it does is it allows us to determine where we put our focus on the display. So I can move the cursor to a certain display, and then I can move the cursor around to interact with certain fields of data.
And it's one of the primary controllers because there are going to be times when we're under 4G, 8G maybe even, and we won't be able to lift up our hands and push the buttons on the display. So this is exactly how we will do it. There is far more information on these displays than we will need to fly this spacecraft normally. But if a system goes off, if something goes wrong, we can dig down into the lowest levels of the computer of all the systems here, and we can take a look, see what's failed, talk to Mission Control in Houston.
And then right next to the displays, you see switches and toggles and dials. And so we call those switch interface panels or SIP panels. If the rotational and translational hand controllers didn't work, we also have a backup to a set of switches.
Hi, my name is Jeff Simmerow, and I work for Lockheed Martin. We're here in the Exploration Development Laboratory, where we do integrated testing and verification of the GNC flight software for the Artemis program. GNC stands for Guidance, Navigation, and Control. Guidance is basically, where do we want to go? Nav is, where are we? Controls is, how do we get from where we are to where we want to be? This is the software that interfaces with both the translational and rotational hand controllers.
We call this whole stack up the Crew and Service Module, or the CSM. That is the crew module, the capsule, the spacecraft Orion, and then the service module. made by our partners ESA and Airbus in Europe. And so this is where the thrusters that will maneuver us on the service module.
My name is Rashid Amikhan. I'm the lead of Assembly, Integration and Test team of Airbus, and we built the European service module in Germany. When the astronaut gives a command to go in any direction, the software is steering every thruster as needed, so it's a balance or a dance between the different engines. So if you provide thrust on one side, you have to counteract it on the other side.
Every time you touch the translational hand controller or the rotational hand controller, those thrusters fire. And those thrusters are right near us, and you can hear them banging. It's like bang, 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 bang as you're flying this thing around.
And I hear it and feel it, and even though it's quite well shielded and that we're in suits and other things, you're still going to hear and feel those thrusters when they fire. It's pretty neat.
Yeah. I cannot wait until one of us takes controls and just steers this thing around and looks out at the Earth.
We'll be farther from the Earth than a human being has been in a very long time.
Let's go.
Let's go.
And liftoff of Artemis 1. We rise together back to the moon and beyond.
I'm not used to talking about trees, like rocks, which is easier. Seeds represent the most optimistic of our species. Given our reliance on wood, from raw material for a home to a baseball bat, and now spacecraft, planting a seedling is an investment in our future. The tree may not bring you fruit, but it will bring future generations fruit. In 1962, President Kennedy said these words: "We meet in an hour of change and challenge, in a decade of hope and fear, and an age of both knowledge and ignorance. The greater of our knowledge increases, the greater of our ignorance unfolds." Artemis 1 continued in the grand tradition of what Artemis 2 astronaut Victor Glover suggested during his visit to Goddard as vessels of humanity, that we take our culture with us into the cosmos. That we should choose to take seeds and plant them for future generations to enjoy, to remind us earthbound explorers that, despite the problems we face here, we remain connected to our future in space. I'm hopeful that all of our shared work on Artemis missions will bring similar fruit to future generations.
Hi, I'm NASA astronaut Tracy Dyson, orbiting 260 miles above the Earth aboard the International Space Station. Tonight is time to come together to appreciate and observe our shared moon. We are blessed on the ISS to be able to observe the moon from space, being situated over the Earth's atmosphere. It's quite a sight to behold. The effect of the moon is most dramatic for us over large bodies of water. When the moon is full, it illuminates the whole surface of the Earth, and the ocean glistens with a beautiful soft glow. Contrast that with a new moon, and the oceans are as black as a starless universe. It's almost as if the Earth disappears. It's crazy. Wherever the moon is in its phase, when spotted, you can hear someone say from the cupola, "Come look at this moon." So my crewmates and I are excited to contribute to work that is stepping stone toward NASA's return to the moon through the Artemis program. Stay curious and keep looking up.
We learned a lot from the Apollo samples, but we still have a lot left to learn about the moon. The Apollo missions visited only a pretty narrow swath of the moon. All the missions were concentrated near the near-side equator. Really interesting and really critical insights were unlocked with the Apollo samples, but we have so many questions still to answer about the moon and the evolution of the moon.
And liftoff of Artemis 1. We rise together back to the moon and beyond.
NASA's Artemis missions are NASA's plan to send people to the surface of the moon. We'll be sending people and roving assets and scientific equipment to, among other things, answer a lot of really compelling science questions. Scientists have a lot to learn about the moon. It's our nearest celestial neighbor here to Earth, so what the moon has experienced, we've experienced. Except here on Earth, we have things like plate tectonics, oceans, forests, people that erase the rock record. Whereas on the moon, that whole record of our planet's history, of the moon's history, is just kind of waiting there at the surface for us to explore. The South Pole, which is where Artemis missions are going to target, is specifically interesting for a couple key reasons. We think there are volatiles at the South Pole of the moon that are not present near the equator. Things like water and water ice that are trapped in the lunar regolith, which basically just means lunar soil, that can easily become untrapped from that lunar regolith, and scientists can scoop up and study for return to Earth. The lunar South Pole is a really exciting scientific target, and it also comes with some challenges for operating. For example, the lighting environment will change drastically within the course of one mission, and even over sometimes the course of one spacewalk. So preparing the crew members, preparing the hardware that we're sending to the moon, and preparing the mission control teams is really, really important. The South Pole Aitken Basin is particularly exciting. We think it's one of the oldest and largest impact basins in the solar system. And if we can get the right rock from the South Pole Aitken Basin and bring it back to our labs here on Earth, we can use that sample to constrain the entire evolution of our solar system and really understand the timing of how the moon and our planet and the entire solar system evolved.
Todos los años, a finales de octubre, hay una noche especial en España. Es una noche en la que decenas de asociaciones astronómicas sacan sus telescopios a la calle. Estamos hablando de la Noche de la Luna, cuando juntos todos comparten su pasión por el cielo. Las personas se acercan, curiosas, y es allí donde empieza la magia.
¿Es aquí?
Sí, por ahí.
Telescopio. Que vas a ver la... Dios, qué chulo. Madre mía, qué pasada, ¿no? Muy rara. ¡Hala! ¡Qué chula! Parece que tengo aquí. Guau, se ve perfecto. Es increíble.
Es casi como si pisara allí. Hombre, está súper chulo. Ahora sí, hagan su verdad.
¡Qué chulo! Está muy chulo. Sí, sí.
¡Guau! ¿Qué pasa?
¡Guau! ¡Qué chulo!
¡Wow! ¡Qué chulada!
¿Le ves los cráteres a la luna?
Sí. Es precioso.
¡Qué chulo, chaval! Párate aquí. Mira por aquí. Espera. Mira por ahí. Así, con un ojo. ¿Qué se ve?
La luna.
La luna, ¿eh?
En la prehistoria, los seres humanos habíamos establecido una relación muy estrecha con el firmamento. Durante cientos de miles de años, cuando todavía no habíamos inventado la escritura, el calendario o la brújula, la lectura del cielo nos permitía situarnos en el espacio y en el tiempo. Conocer el cielo era sencillamente una cuestión de supervivencia. Hemos perdido esta estrecha relación que teníamos con el cielo. Y sin embargo, mirarlo, comprenderlo y estudiarlo nos sigue estremeciendo.
Tío, ¿qué pasa? Es que no parece real.
Hi, I'm Sina from the German Aerospace Center in Cologne, and my favorite way to observe the moon is from my balcony. Beobachtet den Mond.
In 2009, NASA launched the Lunar Reconnaissance Orbiter, a bold mission to map our moon in such detail that future crewed and robotic missions could not only land safely, but also go to scientifically important locations. With the start of the Artemis missions, the future is now, as NASA prepares to send humans to the lunar South Pole. This region is of particular scientific interest because it features areas of extended sunlit illumination and permanent shadow, is known to contain resources like water, and sits on the rim of the oldest impact crater in the Earth-Moon system. Over the years, LRO's suite of scientific instruments has delivered as promised, giving us incredible new views and data on this terrain, helping us build a roadmap for exploration. So follow this series as we take a look at how the LRO mission is laying the groundwork for Artemis science. One of the instruments on LRO is the Lunar Orbiter Laser Altimeter, or LOLA. It provides topographic data on the lunar surface, revealing slopes and surface roughness, helping us create models of lunar gravity and surface brightness, as well as high-resolution 3D maps of the moon. In this visualization, the colors correspond to different elevations found amongst the craters and mountains of the South Pole region. Having accurate elevation data is essential for landing site selection, surface navigation, identifying areas where resources can be found, and planning the design of future lunar infrastructure. In addition, studying the elevation and topography of the moon contributes to scientific research about its geological history, formation processes, and ongoing changes. By analyzing elevation data, scientists can learn more about the moon's past volcanic activity, impact history, and tectonic processes. The global terrain mapping by LOLA also makes it possible to simulate sunlight and shadow on the moon at any date in the past or future. Here, we see a visualization of the region in 2028, depicting the changes in shadowing in 2-hour intervals over the course of the year. This information is vital to Artemis for planning exploration endeavors, since the low sun angles and terrain of the South Pole produce a uniquely challenging lighting environment. In the years since LRO's launch, there have been over 60,000 orbits of the spacecraft and 10 billion laser shots at the lunar surface, making LOLA's data a vital resource for both human and robotic explorers that arrive at the South Pole in the coming years. It's one piece in how LRO is helping NASA usher in a new generation of lunar science.
Olá, eu sou a Mariana.
And I'm David.
E nós gostamos de observar a Lua refletindo no Rio Yarra em Melbourne.
And we like to observe the moon reflecting off the Yarra River in Melbourne.
NASA's Artemis II is the first crewed lunar mission in over 50 years. 4 astronauts will venture around the moon, preparing humanity for a long-term lunar presence for scientific discovery and exploration. The 10-day test flight will demonstrate a range of deep space exploration capabilities with crew. The mission will prove the Orion spacecraft is ready to keep astronauts alive in deep space and allow the crew and ground teams to practice operations essential to the success of future missions. On launch day, the Artemis II crew suits up, undergoes final checks, and rides in the crew transportation vehicles to Launch Pad 39B at NASA's Kennedy Space Center in Florida. Stacked on the mobile launcher, NASA's 322-foot-tall SLS, or Space Launch System rocket with the Orion spacecraft awaits the crew, having made its 4-mile journey from the vehicle assembly building on the crawler transporter to the pad. The launch team fills the SLS propellant tanks with over 700,000 gallons of liquid oxygen and liquid hydrogen and verifies guidance, communications, and avionics. At 12 seconds before liftoff, the hydrogen burn-off igniters fire. About 6 seconds later, the rocket's 4 RS-25 engines ignite. When the countdown reaches 0, the umbilicals retract, giving SLS and the crew in Orion the clearance to begin the journey. The 6 million-pound moon rocket produces 8.8 million pounds of thrust to accelerate towards space. 75% of this power comes from the 2 17-story solid rocket boosters, each producing 3.6 million pounds of thrust. About 2 minutes in, the boosters are released, their solid propellant consumed. The core stage and its RS-25 engines continue to propel Orion and the crew to space. After 3 minutes, the protective fairings surrounding Orion's service module are ejected, exposing its solar arrays. 6 seconds later, the launch abort system is ejected from Orion. The crew has safely reached Earth orbit, though they could still abort using service module engines. About 8 minutes after launch, the SLS core stage engines shut down and the interim cryogenic propulsion stage, or ICPS, and Orion separate from the core stage. Orion and the ICPS are now flying free. Orion's 4 solar arrays deploy, powering the spacecraft and charging its batteries for when it moves out of direct sunlight during the journey to the moon and back. After a 90-minute orbit, the engine of the rocket's upper stage, or ICPS, ignites to raise Orion to a high Earth orbit. The Artemis II crew and Mission Control in Houston then began a nearly 24-hour systems check while the astronauts are still relatively close to Earth, familiarizing themselves with their new home for the next several days. Once in high Earth orbit, Orion separates from the upper stage. The expended ICPS and Orion stage adapter serve as a target for a manual handling test called the Proximity Operations Demonstration, preparing future crews for rendezvous, docking, and undocking with other spacecraft. During the demonstration, Artemis II astronauts use cameras and line of sight through Orion's windows to pilot the spacecraft as they approach and back away, assessing Orion's handling qualities, hardware, and software. Following the demonstration, spacecraft data is collected to verify system performance, such as life support, communications, and navigation, ensuring Orion and the crew are ready for the voyage ahead. About 23 hours later, Orion's service module performs the Translunar Injection Burn, or TLI, pushing Orion out of Earth orbit and on an approximately 4-day trip to the moon. Ultimately, the crew's figure-8 flight path extends more than 230,000 miles from Earth. During the trip, the astronauts continue to evaluate the spacecraft systems and practice emergency procedures like testing the radiation shelter. The Artemis II crew travels about 4,600 miles beyond the moon, becoming the first humans to lay eyes on the lunar far side in over 50 years. Their observations will help us prepare for future missions at the moon. During this period, there will be an anticipated communication blackout between Mission Control and the spacecraft. As the crew returns from the far side of the moon, Orion is drawn home by Earth's gravity in a free return trajectory, ensuring a fuel-efficient 4-day trip. Before entering the atmosphere, Orion's crew module separates from the service module. 12 thrusters ensure Orion is properly oriented at an altitude of about 75 miles from Earth's surface. Orion and the crew enter Earth's atmosphere at a speed of nearly 25,000 miles per hour. Decelerating at a rate up to 4 times the force of gravity, the crew will feel 4 times heavier than they do on Earth. Orion's heat shield protects the spacecraft from temperatures of about 5,000 degrees Fahrenheit, about half as hot as the surface of the Sun. To slow its descent, Orion begins a precise deployment sequence of 11 parachutes. 3 forward bay cover parachutes first separate the protective thermal cover that sits over the chutes. 2 drogues slow and stabilize the crew module, then cut free. 3 pilot chutes lift the 3 main parachutes, deployed at an altitude of 9,000 feet and traveling 130 miles per hour. These chutes slow the crew module to a speed of less than 20 miles per hour. After traveling more than 595,000 nautical miles, Orion splashes down in the Pacific Ocean, about 50 nautical miles from the California coast, just 16 minutes after entering Earth's atmosphere. After splashdown, a recovery team that includes the U.S. Navy, Air Force, and NASA approaches Orion. The team ensures it's safe for the crew to exit before divers help the astronauts onto an inflatable front porch, hoist them into helicopters, and fly to the recovery ship. Orion is towed into the ship for its return to Kennedy Space Center. Their mission complete, the crew is flown back to land and step on solid ground for the first time in 10 days. This is Artemis 2. Learn more about Artemis at nasa.gov/Artemis.
Aloha, o ku'ulei kia. A ke kilo nei wau I ka mahina, mai imi loa ma Hawaii mo kupuni aku.
There's been a lot of excitement about spacesuits lately. But what about that iconic puffy marshmallow suit that we used to walk on the moon? This is what we call an extravehicular mobility unit, or EMU, and these suits truly are in a class of their own. Since Apollo, we've retooled and reimagined what can be accomplished on a spacewalk. And the current spacesuit that NASA uses is based on a design that first flew in 1981. Through rigorous maintenance, safety testing, and upgrades, this suit has allowed us to perform some incredibly monumental achievements and spacewalk our way into the record books.
We may have all come on different ships, but we're in the same boat now.
A spacesuit is not something you simply wear. It's more like an astronaut's very own personal vehicle.
A spacesuit is basically a self-contained environment. It is a mini spacecraft that is tightly wound around a human body,
containing everything they need to survive. Because we are going back to the moon and onto Mars. Exploration spacesuits have to solve the challenges from the past and anticipate those in the future.
Some of the biggest environmental challenges that we're seeing is finding a balance between mobility and lunar dust.
In other words, exploration is dirty work.
Looks like you guys have been playing in a coal bin. I don't know how we will get it out. Let's do the best we can, yeah. Like, how are we going to clean these guys off before they're allowed to go back inside? There's many ways, and do we know if they work? We have to find out.
And when your life depends on a good seal and perfectly performing fabrics, dust is kind of a big deal.
Lunar regolith, it looks like it's just a fine-grained material when you see the pictures of the Apollo boots in it and stuff. But you're going to see anywhere from broken rock shapes to fractured glass shapes. That's what it looks like under the microscope, of such a small particle size range that it gets in everything.
The Apollo missions only needed their suits to last for a few moonwalks. But these missions to the moon and Mars could be weeks, months, and even years long, demanding the most innovative solutions from NASA and our industry partners.
Whether we put a protective layer, whether we are able to charge the suit to repel dust, there are multiple things that we're looking at, so we still have a lot of challenges and work.
The original EMUs were designed for the astronauts of that era. Since then, our astronaut classes have become far more diverse, and the next generation of spacesuits can follow, well, suit. As NASA works together with industry partners on exploration spacesuits, follow along and be part of our journey to the moon and beyond.
Thank you so much for tuning in to this year's Air National Observe the Moon Night Show and for celebrating the moon with us, wherever you may be. Wishing you clear skies and see you on September 19th, 2026 for the next Air National Observe the Moon Night. See you later.